So now we're going to talk about chapter 11, which is about upgrading Bitcoin. And this is probably, might be one of the hardest chapters so far, maybe. But upgrading Bitcoin. First, I need to define a word that I call a fork. A fork is a change of Bitcoin's consensus rules. And that requires the definition of consensus rules. And the definition of consensus rules are what the consensus rules define what a valid blockchain is. And thus, a fork changes the definition of a valid blockchain. So this is my definition of a fork. The word fork is used by people in different contexts. For example, you can fork a GitHub repository. Or you can, and some people even say that a split in the blockchain is a fork. But I give the word fork this very specific meaning. So a fork changes the definition of a valid blockchain. So it is a software change that changes the rules, the consensus rules. There are other changes of the software that aren't forks at all. For example, if you change the relay policy for nodes, whether they should relay a transaction or not based on some new rule, that doesn't change the consensus rules. It doesn't change what a valid blockchain is, only how peers communicate. And there are two types of forks. There are hard forks and soft forks. Hard forks relaxes the rules so that after the hard fork, the set of valid blocks increases. And a soft fork tightens the rules so that the set of valid blocks decreases. So this is an illustration of that. You have the old rules in the middle, and as an example, we can take the block weight, which is now, after Segwit, the block weight is limited to 4 million bytes. 4 million weight units. And if we would make a rule change that says that the block weight is increased to 8 million weight units. So the block must not weigh more than 8 million weight units. That would be a hard fork because you relax the rules. And contrary, if you make a new rule instead that would limit the block weight to 2 million weight units, that would be a tighter rule, and thus it's a soft fork. So these are the two types of forks. So let's take this weight unit limit as an example for a hard fork and see what happens. So suppose that you create a new version of the software where you change this rule from 4 million weight units to 8 million weight units. So you relax the rules, you create a hard fork. So let's see how that would play out if you just roll out your new software, and maybe you are the only miner who runs this new software. So you have a minority of the hash power, and see how that happens. So you roll out your new code here somewhere, and the old miners, they don't know anything about your new rule, so they will just keep building their blockchain. And as soon as you create a new block that's bigger than 4 million weight units, but still less than 8 million, so it's valid according to your rules, but it's invalid according to the old rules. So when you create this block and try to publish that, no one will accept it. So old nodes will ignore your block. And they will keep on building on their blockchain without your block in it, like this. And you, during this time here, you have one block each. Your blockchain is here and the other blockchain is here. At this point, you keep trying to build blocks here. But since the old chain is stronger, they will probably produce blocks faster than you. So at one point, this old blockchain will create a new block here. And at this point, this blockchain is stronger than this blockchain. And keep in mind that this blockchain is valid according to your rules. So you will switch back to this blockchain here and start building from this block. So you are rejoining this blockchain. And the old nodes and you keep working on this blockchain. So new blocks are created, and here at this point, you happen to create a block, but this block isn't bigger than 4 million weight units. So this block is then valid both according to your rules and according to the old rules, which means that old nodes will accept your block here. So but that's just because you happen to create a block that's small enough. And then the old nodes will continue building on you and all the others will continue building on your valid block here. And at one point later, you happen to create a block that's bigger than 4 million weight units again. So the pattern repeats here, and the old nodes will ignore your block, and this pattern will repeat. And as long as the old nodes are in majority, you will keep being wiped out like this. Your branch will keep becoming stale. And you will go back to the main branch, to the old branch. And this is as long as the old nodes are strong or have more hash power than your branch. Suppose instead that you create this new hard fork, but you also convince a lot of miners to use your new software. What would happen then? So you have this old software here, and you roll out your system here, your new software here, and a lot of miners starts adopting it, but not all. So you have a majority hash power on your new software. And you create this new block here, which is bigger than 4 million weight units, which is ignored by old miners. But since you have a stronger, more hash power, your branch will become stronger over time than the old branch. So at this point, it seems like old and new nodes seems to have parted forever. So now you have effectively two blockchains. You have effectively created two lasting currencies. But this is only so as long as you keep the majority of hash power on your branch. So suppose now that some miners on the new branch decides, no, we want to go back to the old nodes. This was no good. So suppose that the majority of the hash power switches to old at this point, then the old node will grow faster than your branch. So and at some point, the old branch will even be stronger than your new branch, and at that point, your new blocks will be your the new miners will switch to this branch because this branch is valid according to them, and so they will switch back to the old branch. And that would mean that this whole long branch here of 6 blocks in this case will be wiped out. They will be stale and the work will continue over here. So this is a real risk, right? So all the money spent to create blocks here, all the electricity spent here will be wasted. And also the ones, because the ones who have created these blocks will lose their coin base, because their coin bases are not part of the strongest blockchain, right? If it's not part of the strongest blockchain, they don't exist. So at this point, we are back, everybody's back at the old branch, even your software. And then you might, again, restart the chain, the new chain, if you mine a bigger block here, and the pattern might repeat. So this is a problem. And if you want, as you see here, you are being wiped out here. This branch is being wiped out by the old branch. If you want to make a hard fork, it's then suggested that you use something called wipeout protection. So one particular cryptocurrency called Bitcoin Cash made a hard fork back in 2017 for various reasons, but no good reasons if you ask me, but they decided to do this. And I'm not endorsing Bitcoin Cash in any way. I'm just explaining here how they used wipeout protection in order to not be wiped out by the main Bitcoin branch. Because Bitcoin Cash was had a minority hash rate compared to proper Bitcoin. So what they said is that at this particular height, 478,559, the block at this height, according to the new rules, to the Bitcoin Cash rules, was that the block must be bigger than 1 megabyte. And this was before Segwit also. Actually, let me get back on that, or just ignore that. So what they required is that the block at this particular height must be bigger than 1 megabyte. And as we know, the old rules say that blocks must be less than 1 megabyte, or at most 1 million bytes. So when Bitcoin Cash started, it wasn't allowed to make this block less than 1 megabyte. And eventually they managed to create such a block. And that was the first block this was the first block of this Bitcoin Cash split. And then the following blocks after this block can be of any size. But what happens then is that this new branch here can't be wiped out now, because this block is invalid according to the Bitcoin Cash rule, because it's less than 1 megabyte. So this branch cannot be wiped out by Bitcoin. So that's how they solved it. And again, I'm not encouraging the use of Bitcoin Cash, but this is just an illustration. Okay, so this was hard forks. And let's now have a look at something called soft forks. And as I said before, soft forks tightens the rules, so fewer blocks are valid. The set of valid blocks decreases, shrinks. As an example of a soft fork, we have Segwit. And the important thing with the soft fork is that old nodes must accept Segwit blocks. But they don't have to verify all aspects of the block. But the important part is that a block that's valid according to Segwit rules also need to be valid according to the old rules. And of course, new nodes must verify all aspects of Segwit. But also, there are problems here. Old nodes can create blocks that are invalid on new nodes. And we talked about this in the main room just before this lecture. So old nodes can create blocks that are invalid on new nodes. For example, an old node that doesn't know anything about Segwit can accept a transaction into a block that spends a witness output, like a Segwit output like this, without a witness. So an empty signature script. And we talked about how this is valid according to the old rules. It's just a non-zero element on top of the stack when you run this script program, which makes this valid. So they create a block with this transaction in it, with this here transaction in it. Let's see what happens. And suppose that most miners are still running old software. This is not how it happened, but suppose that this would happen, that just a few miners are running Segwit and most miners are running old nodes. So old has more hash power than new. And this old miner will mine a block that's invalid according to Bitcoin New because they include this transaction here. And this is then, of course, invalid to new nodes. So new nodes will not mine on top of this block here because it's invalid. Okay, so the new nodes will keep mining on this block here, and eventually they will find a block too. But this is not according to old nodes, this is not the strongest blockchain, and not even this is the strongest blockchain. So old nodes will keep mining on their old chain, and new node will keep mining on their chain, because that's the strongest valid chain according to them. Remember, this chain is invalid according to the new nodes. So now it seems we have a lasting split, a long-lasting split here. As long as the old has more hash power than the new. So this is a big problem. We don't want this to happen. But suppose now that the situation changes and old nodes decide that they want to start running the new rules, Segwit. What would happen then? So now the tables have turned. So now new has more hash power than old. And as time goes, the new chain will get more blocks over time than the old chain. And at this point, the new chain is stronger than the old chain. And at this point, all old miners will move over to this new chain here. And from this point, everyone will be working on this chain. Of course, it can happen again that an old node creates an invalid block. And if that happens, it will probably be wiped out pretty quickly because the new branch is stronger. Okay, so this is what could happen if you deploy a soft fork without having broad support for it. So this is what happens when you deploy a soft fork without having broad support for it. And this is how it could play out, but even the slightest split will cause some stir in the community and in the markets. So this will probably be very bad for Bitcoin, especially the price of Bitcoin. So I also want to say that, yeah, all right. So in the event of a split like this, if we have a lasting split, we run into a big problem. Suppose that you have, even though it doesn't matter if this is a soft fork or a hard fork, we have a fork and which has resulted in a split like this. And suppose that you have one UTXO with 2 BTC in it in this blockchain here, in this block here. Then after the split, you would have the same UTXO here and here. So you will have like 2 copies of the same UTXO, 1 copy on the old blockchain and 1 copy of the new on the new blockchain. And you will keep this UTXO on each blockchain. So what happens when you try to spend this on the old chain? You want to spend your UTXO here. What will happen? Yeah, you will create a transaction that spends this UTXO on the old chain. So this transaction ID and this index here points to this row in the UTXO set on the old branch. But the problem here is that it will also point to this row here in the UTXO set of the new branch. And when that happens, when you publish this transaction on an old node or on the old network here, if this transaction ends up on new nodes, it will be valid there too. So this transaction, if confirmed here, or if published here, it may also be published here. And they are valid on both blockchains. So this is not what you intended. Now this transaction will be confirmed on both blockchains. And you only intended to spend your old coins, not your new coins. So this is what's called transaction replay. You can take a transaction from one side of the split and replay it on the other side. But yeah, right. So what you can do to avoid this is to make the transactions mutually exclusive. And for example, I'm bringing up Bitcoin Cash again reluctantly, but it's an example of how a hard fork can prevent this from happening. So did I write anything about this? Yes. So what they did is that they changed the signature format in a slight way so that it's invalid. Their new signature format is invalid on proper Bitcoin and is required on Bitcoin Cash. So signature on Bitcoin will not be valid on Bitcoin Cash. And a signature on Bitcoin Cash will not be valid on Bitcoin. So that's how they did to prevent this from happening, So we're going to talk a little bit about upgrade mechanisms now. We have only talked about the dynamics of forks and how splits may occur when you deploy new software. And as we have seen, it's really hard to deploy software without causing a split. So Softworks, when you upgrade software, when you make a fork, a soft fork is generally preferred because old nodes will keep on working and follow the new chain if it's stronger. This means that you won't split off old nodes. And to avoid a split during a soft fork, you need majority hash power. So, because a long-lasting split is a serious problem in Bitcoin, and even a short split is a problem. And repeated short splits is also it's an even bigger problem. So you really need the majority of hash power to support your new feature, to support your soft fork before you activate it. So an upgrade mechanism should try to avoid a split. That's very important. So let's have a look at some historic upgrades. So in 2012, pay-to-script hash was introduced to Bitcoin, and it's defined in BIP 16. And this was a manual process, more or less. So hang on. Yeah, this was a manual process. The developers said that, okay, if the developers contacted miners and said, please support pay-to-script hash. Please signal for pay-to-script hash by adding this particular string in your Coinbase input. As you recall, this can be anything here. I support pay-to-script hash, for example, and it can be Lisa was here or anything. But if they include this string in their Coinbase input, that would mean that they signal that they want to support pay-to-script hash. They don't enforce pay-to-script hash yet. Pay-to-script hash is not rolled out yet. This is just a signaling mechanism for miners to signal their support for a future upgrade. And then on a specific day, they looked at the last 1,000 blocks and counted how many of those 1,000 blocks were signaling for pay-to-script hash. And they had set a threshold for 550 blocks. So if more than 550 blocks would signal for pay-to-script hash, then they would activate it at some point in the future. So when they counted, they could conclude that they had more than 550 blocks. So they had more than 55% of the hash power supporting this change, this upgrade. And so when they had counted this, they created a new version of the software, which implemented pay-to-script hash and said that in the software, the software would automatically start activating this pay-to-script hash rules on April 1st, 2012. So they rolled out this software and people picked it up and started using it. And this went smoothly. It went well, even though they only used 55% signaling as a threshold, which was, I mean, it's not totally convincing. You would probably need a more overwhelming majority for this, to do this. This was, I think, a bit reckless, but it worked out. So this was a very manual process. And then for the coming upgrades for other features, they started looking at how can we do that in a more automatic fashion. So they started looking at something called the block version number. And I haven't been totally honest with you so far. The block header contains a version, and I haven't mentioned it yet. but I do now. So there's a 4-byte version at the very beginning of the block header. And from the beginning, this version was 1. And the developers thought that they might use this version to upgrade Bitcoin. So, for example, at one point, they wanted to make a change to Bitcoin that's according to BIP 32, which is named height in Coinbase. And the idea here is that the Coinbase must include its the block height of the block. So if this block has this height, the Coinbase must also include this height here. And there is a reason for this. I won't go, maybe, well, I won't mention that, but this is at least what BIP 34 says. You need a height in Coinbase. And it also says that to deploy this, we are going to use these version numbers for signaling. So a block that uses version 2 must have height in Coinbase, but it's not enforced immediately. It was enforced in gradually or in steps. I will show you. So it started out with new miners would signal for this using the higher block version. So miners would set block version 2. That's all they did on this first step. And then the software would wait until 750 out of 1,000 blocks have version greater than or equal to 2. And at that point, when that threshold is reached, you can be pretty sure that the new miners have about 75% hash rate. But you can't be totally sure, because there can be false signalers. I mean, people might have set a higher block version even before this BIP. So to rule out false signalers, you started at this point when you have reached this threshold here, 750 out of 1,000 blocks. The software will start rejecting version 2 blocks that doesn't have height in Coinbase, and that would remove most of the false signaling blocks. I mean, miners who would signal use version 3 or 2 for other purposes would be invalid. And then you would wait until 950 blocks out of 1,000 blocks have version greater to or equal to 2. And at that point, when this threshold is reached, the node will start rejecting all version 1 blocks. So if a block producer produces a version 1 block, it will be a loser block. No one will build on top of that block because it's invalid according to 95% of the mining hash power. All right, so that's version signaling. And this was used by a few different upgrades. BIP 34 that we just talked about, and then we have BIP 66. Remember, I talked about the strict DER encoding to avoid transaction malleability. So this was an early attempt at least removing some of the malleability possibilities. And this one used version 3 to signal. And then we had BIP 65, which you can read about in chapter 9, check lock time verify, used block version 4, using the same rollout mechanism. But there are problems with version increments like this. The first one is that you can only deploy one feature at a time. So if you wanted to deploy 2 features, independently, you couldn't vote for only one of them. Or if you have version 5 and 6, for example, maybe you want to vote only for version 6 but not version 5, then you couldn't do that. So that's a bit of a problem. And also you can't reuse old versions, because these versions are only used for the upgrade mechanism itself. After the upgrade has been successful, you don't need that version number anymore, actually. But yeah, so there are problems with this, and we're going to solve that after the break. Yeah, so before the break, we talked about the problem with the version increments as a signaling mechanism. And so developers started looking at alternatives. And they came up with this idea that they start using the version number differently. As you recall, the version number is a 4-byte integer, which is 32 bits, like this. And they said that if we want to roll out a new feature, the top 3 bits must be exactly 001 and followed by a sequence of 29 bits. And each bit can represent a single feature or a single upgrade. So in this example here, we use bit 10, counted from the right here, 0, 1, 2, and so on. So bit 10 is used for this particular upgrade in this example. And what we can say about this here is that this number that we see here, suppose that this was a 0, sorry. Suppose that this is 0 now. Then this number would correspond to, 2000000, which is definitely bigger than 4. So we still fulfill the requirement that the block header must have version bigger than 4, or at least 4. So it is bigger than 4. So we follow that rule. That's good. And it also supports 29 independent feature upgrades. So now we could deploy features independently from each other. So one means that the feature is enabled, or not the feature, but the upgrade mechanism, the feature that you want to signal for is enabled, or the signaling for that feature is enabled here. Yeah. So when you want to make a deployment, you need to specify a few things. You need to specify a name for this deployment, and which bit of these 29 bits, and you need a start time and a timeout. And given this information here, you have this state diagram that you follow through, that you go through with, or that you use for upgrades. So if you want to make an upgrade, you specify these things, and it will always start in the defined state here. And after each 2016 blocks, after each retarget, you make a transition to another state or the same state. So you can only transition on after every retarget period. So we start in the defined state, and as long as the start time hasn't passed, we will stay in defined state. And if the timeout passes, we will enter the fail state. And fail state means that if this deployment failed, we will we will not be able to upgrade this time. We might make a new try at the later time using probably another bit, but at this time this deployment is definitely failed, and once failed it will stay in the failed state always. But if the start time has passed and we haven't passed the timeout, so if the start time has passed, we enter the started state. And we stay in the started state as long as less than 95% of the blocks in the last 2016 blocks. 95%, if less than 95% of the last 2016 blocks signal, we will stay in the started block, in the started state. And also the same here, if timeout passes, we will enter the failed state. So as long as we don't have enough signalers, we will stay here. And when 95% is reached, we will enter the locked in state. And this is the point of no return. When you enter this state, you know that it's going to activate. And then it will activate automatically after 2016 blocks. In the next retarget, it will activate. So this locked in state here is to, so when we reach the active state, that's when we actually enforce the new rules. So that's when we enforce the rules. And the locked in state is to give remaining miners, the remaining 5% of the miners, to give them a chance to upgrade before it activates. And you could argue that this is a pretty short time, and that's probably true, but they had all this time here and here to do it, but they refused. And so we give them one last chance here to upgrade. So when we reach the active state, we enforce the new rules and we stay in this state forever. And note that when we compare things about time, you know, when the start time has passed and timeout has passed, these checks are made against the MTP, median time passed. And that's important. Right. Yep. So let's have a look at an example of how this was used in reality. And we're going to use BIP68 as an example. BIP68 is a way to lock outputs for a certain amount of time before it can be spent. Check sequence verify, CSV, as you see here. CSV means check sequence verify. And this is it's more than an opcode, but the general idea is to add an opcode to the scripting language so that you can prevent an output to be spent until a certain point in the future, or relative. It can't be spent for before, say, 10 blocks has passed after this output was confirmed. So that's used for various purposes. You can read more about it in chapter 9. But anyway, it's not just BIP68. There's a group of BIPs, BIP68, 112, and 113. Those three together were deployed together because they are tightly related to each other. Anyway, so as parameters for this BIP9 deployment, we use the name CSV, bit 0, and the start time of 2016, 1st of May, midnight, and the timeout exactly 1 year later. Okay, so we're going to see what happened. So we have this, as always, they are starting in the defined state. And on the 11th of May, it transitioned to started at this particular block height. And then we stayed here for 3 retarget periods because we hadn't reached this threshold. And after 3 retarget periods, we had more than 95%, which means that we transitioned to lock-in, which is point of no return. And then in the next retarget period, we activated this CSV rules. So this went very well, actually. Everybody was happy about this. So, and then in 2017, we wanted to use this BIP9 deployment again. This time it's Segwit. And the BIPs that were deployed is 141 and 143. And we set the parameters to Segwit and the bit1. I say we, I wasn't involved that in that way, but I say we, I just use we as a pronoun here. So we use Segwit and bit1. Start time was 15th of November 2016 and timeout 1 year later. So let's see what happened. So this is what happened. We started in the defined state, and when the start time has passed, we moved to the started state, which happened on November 18th. And then we got stuck here. Retarget period after retarget period. We got stuck at about 30% miner support, which was a great disappointment, actually. And what actually caused this is not entirely clear to me, but there was a lot of drama regarding block size, regarding comments on how Segwit would kill Bitcoin, or how, yeah, a lot of stuff. There were powerful people with agendas that wanted to not deploy Segwit in this way. So this is what happened. So we got a lot of drama, and miners were reluctant to signal for Segwit. And we had some more drama. And I won't go into all the details of the drama because this was a very, very complex scene. But eventually, Segwit activated after a lot of time. As you can see here, it took until August for Segwit to actually activate. And of course, the reasons for this are many. And I shed some light on it in chapter 11, but if you really want to dig into this, what actually happened, you have the book called The Block Size Wars. Sorry, it should be one word here, but the block size wars. There's a whole book on this subject. Actually, it's not only on Segwit. This book covers, I guess, the whole history of the block size debate. And I haven't read this book myself, but I heard that it's good and very interesting. And if you want to know more about Segwit in particular, I suggest that you read a good article by Aaron van Wirdum of bitcoinmagazine.com, The Long Road to Segwit. You can just search for Bitcoin Magazine, The Long Road to Segwit, and you will find it. It's worth the read. So I won't dig into the details of how Segwit was deployed. but we learned a few lessons during this deployment. So first of all, 5% of the miners can veto a BIP9 deployment. Of course, this was already known before, but I guess it hadn't really got to people. So it became very obvious now that this might be a problem when you want to make upgrades. I think we were naive when we started the deployment of Segwit a bit. And also that we pay miners to perform correct, honest transaction confirmations, and we don't pay them to decide the rules. We pay them to follow the rules. So it's not the miners who decide what rules to run on the Bitcoin network. It's you and me who decide the rules that we want to use on our own full nodes. That's the important part. So rules are decided by its users, you and me, and it's not the miners alone who decide this. Well, of course, miners are also users, so they, of course, get to choose their node of choice. But we will have a look later, soonish, on the incentive structure here. So we want to talk about, I want to talk about user-activated soft forks. This BIP9 stuff is what we call a miner-activated soft fork. It relies on the miner's good faith to signal for stuff that users want. But in the case of Segwit, it became obvious that miners didn't signal what users want, because the users, an overwhelming majority of users, wanted Segwit, but the miners wouldn't. So people started discussing user-activated soft forks. And if we take just an example here, suppose that you have a soft fork and 99% of the non-miners want smaller blocks. The soft fork is that you want to make blocks smaller. And suppose also that 99% of the non-miners want this soft fork. And also suppose that no miner wants this. They won't comply with this new limitation, this new soft fork. So non-miner, and also suppose that non-miners will start rejecting big blocks after a certain height. So after height X, users will start rejecting any block that's bigger than that's too big. I just say smaller blocks here, but let's call it small blocks and big blocks. So the important thing here is that users will start rejecting big blocks after X. See what happens. And suppose that this is time X here. So up until this point, everybody agrees, and we have this block here. And now users are waiting for a valid block. And the miners continue as they always have done. They don't use this new software, so they create a block as they always have, and this block happens to be big. So it will be rejected by the users. So the users are still waiting for valid blocks here after this block. But the miners will keep building their blockchain like this, which is, of course, invalid for the users. And what happens to the miners in this case? So, as I said, all users are using small blocks, are refusing these big blocks. And users, that can be an exchange, for example, or an electricity company, or anyone that's not a miner. So in this case, miners can't pay for their electricity because the electricity company won't accept their coins, because their coins doesn't exist on the valid blockchain. I'm gonna emphasize one thing. Suppose that they are trying to spend their coin bases. So this Coinbase here, which is invalid according to most users. Suppose that some point in the future he wants to spend this coin to pay for electricity, for example. He won't be able to do that because that coin doesn't exist according to the electricity company. And they also can't exchange this coin for other currencies because the exchanges are users also, and they will not accept this coin. And furthermore, the value on the miner chain is unknown. I mean, no one trades them. So what value do they have? So that is unknown. So there are a lot of problems here lots of problems for the miners. And eventually miners will start to run out of business. I mean, they have a mining operation that's really expensive to run. And if they can't pay their electricity bills or pay salaries, they will run out of money. So they will run into problems. But imagine now that one small miner decides to, okay, let's skip this. I'm going to the users branch. I'm going to upgrade my software to the users branch. So this miner does that and creates a block. And the nice thing here is that during all this time here, users here are getting frustrated because no new blocks are coming in. And they see a huge pile of unconfirmed transactions piling up in their mempools. And when you have a lot of transactions wanting to confirm, it will also mean that the transaction fees will start to rise, because the more transactions waiting, the more competition it is to get your transaction confirmed. So the higher fee you pay, the more likely it is that you get into the next block. So this would push up transaction fees a lot. And so this block here will be really profitable for this first miner coming here. And hopefully he will be able to save his business thanks to this. And eventually the other miners hopefully will start converting too. So we have this situation that at some point enough miners move over to the new branch, and the new branch will eventually outpace the old branch, which will then force these miners over. So here at this point, this new branch is stronger than the big block branch, which means that the big block branch will be wiped out, and the old miners will move over here and start mining here again. So and if they are wiped out like this, even if they had a Coinbase in their blocks, their Coinbases will be, wiped out too, even on their own chains, so to speak, even on their own software. Okay, so this was this was a little lecture on user-activated soft fork and how that might turn out. We haven't used this really. but it's a constant discussion. It was absolutely a big discussion during the Taproot upgrade. How do we, what upgrade mechanism should we use for Taproot? And this is not covered in the book because Taproot didn't exist back then when I released this book. So I have made some slides on this, and one ugly picture that's not made by a professional illustrator. So the Taproot upgrade. So Taproot is a new major upgrade. It's the next version of Segwit. So it's version 1 Segwit. The previous version was version 0. So there were a lot of discussions on how to deploy Taproot. And BIP9 wasn't good enough due to this minor veto issue. And some people argued that the user-activated soft fork was a bit too risky, according to some, because they didn't want this split to happen. Yeah. So there was a new BIP 8, that was discussed. BIP 8 is actually a BIP that came during the Segwit drama, but wasn't used back then. So Segwit has, or BIP 8 has evolved a bit since then. And it basically means that miners can activate if a certain threshold is met. It works like BIP 9 in that way. So if miners collectively signal enough, then the fork will activate. But if miners don't activate, there are two options. You can have one parameter, one deployment parameter that's called LOT, lock-in on timeout. If lock-in on timeout is true, this means that users will enforce the new rules on a flag day sometime in the future. That's predetermined. And if LOT is false, it means that the deployment will fail, just like in BIP 9. So LOT equals false means that it's a miner activated soft fork. And lock-in on timeout is some kind of user activated soft fork, but miners can activate it early only. They can only make it earlier, but they cannot prevent it. So again, there was a lot of drama, but this time around the deployment parameters themselves, and especially the LOT parameter, lock-in on timeout. So lock-in on timeout equals true means miners don't decide the rules. And LOT equals false means, well, miners do decide at this time. So if we use LOT equals false and we let the deployment fail, if not enough signaling, we will have the chance to start a new deployment, maybe this time with the user activated soft fork. So due to this drama, someone had to come up with something that everybody could accept. Yeah, and of course the drama was about having LOT equals true or LOT equals false. So that was the big drama. So someone came up with a suggestion that attracted both camps. It would use BIP 9, and it's called speedy trial. So it was a BIP 9 deployment, and it would use bit 2 and the name Taproot, and it would have a start time on April 24th and a timeout on August 11th. as you can see, this is a pretty narrow time window here: April, May, June, July, 3.5 months or so. So this is about, this should cover 6 retarget periods only. And we also adjust the threshold from 95 to 90%. And if miners decide to activate this, if miners signal, if 90% signal, then the activation will happen on November 12th, 2021. So we have a much longer lock-in period. So we changed the locked-in period to be locked in until a certain date has passed. Because we use this because if miners wouldn't signal, we would get a very quick response for that, since the timeout is short. And so this was a way to quickly measure miner sentiment for this. And if they would fail, the developers could go back to the drawing board and find some kind of other solution. But if everything was kumbaya, it would work out fine. And this is my ugly picture that I made yesterday for how Taproot deployment worked. So as all deployments, they start in the defined state. And on May 1st, it transitioned to started. And it stayed for, I think it was 2 retarget periods. 5, let's see here. May 1st, it's 3 retarget periods actually. So after 3 retarget periods, this transition to lock-in. So we are now in locked-in. So this activation method worked, and we are now in locked-in and waiting for the November 12th, when this soft fork will activate, when Taproot will activate, and then we will stay in that state forever. So the rules will start to be enforced in November. So that's good. This worked out fine. So it seemed like it was a good idea to use this speedy trial to quickly get an idea on where miners were standing on this. So I think that's it for chapter 11. And when we do the exercises, I want to warn you about exercise 11.8, because that is horribly hard, and try it at your own risk. But by all means, try. But it's horribly hard. If you manage to solve that, I'm impressed. And if not, please check it out in the answers section in Appendix B.